Hello again, everyone, or hello. Welcome to this session. So this is the last session of the day. We will wait a couple of minutes before to start, as many of you are still getting connected. Okay, so I think we can start the introduction now. Welcome again, everyone. So I'm Corentin Jouvet from Power6. And for this session, I'm very happy to welcome Dr. Yu Wang from the University of Sheffield. So you will talk to us about the investigation of unbalanced magnetic force in fractional slot permanent magnet machines with odd number of stator slots. So Dr. Yu Wang was born in Zhengzhou, China in 1991. He received the Bachelor of Engineering and Master of Science degrees from Nanjing University of Aeronautics and Astronautics in Nanjing, in China in 2013 and 2016, respectively. And he got also the PhD degree from the University of Sheffield, in Sheffield in UK, in 2019, all in electrical engineering. Since 2019, he has been with the Sheffield Siemens Gamesa Renewable Energy Research Center in Sheffield, where he is currently a research associate. His research interest includes the analysis and design of novel permanent magnet machines for high-speed and wind power generation application. Since August 2019, he has been appointed as the chair of IEEE, the University of Sheffield Student Branch Joint IAS PELS chapter. So during this presentation, you will be able to ask questions to Dr. Yu Wang. So for this, please use either the chat panel of the presentation or the Q&A panel. It's up to you. After the presentation, we will keep some time to answer this question. So please ask them when you want, and we will collect all of them and make sure we answer them by the end of the presentation. Okay, so I think it's your turn. You can share your screen now if you are ready, of course.
So, can you see my PPTs on the screen?
Yes, we can see your screen. It's okay.
Okay, so shall we start now?
I think you can start. Yeah.
Okay. Okay, thank you. So I'm very glad to be here to share with you my presentation today, which it has the topic of the unbalanced magnetic force, which is short for UMF. So today we are only going to talk about this UMF in fractional slot PM machines, which has a odd number of stator slots, which is a special type. So the main logic of today's presentation will mainly focus on three questions. So these three ones are: when will the UMF, which is short for unbalanced magnetic force, happens? So when it will happen? So this is the first question. And the second one is how this UMF is influenced. So that means how those, when it happens, how it is influenced by the specific machine topology, such as the slot and pole combination, such as these things, how it is influenced, how large or how small is of this UMF. This is the second question. So the third question is how to mitigate the UMF. That means in some cases, if when we are about to have the UMF, how we can reduce them, how we can make this UMF as low as possible. So this is the third question. So let's look at the first one. First, we will have a brief introduction of the whole research. So this is the fractional slot PM machines. We know that which is short for FSCW, which is means because fractional slot PM machines with always comes with the non-overlapping windings, or we say concentrated windings here. So they are actually these type of machines are widely used in a variety of applications. Here we can see it is used in the electric vehicle traction, which is like the Nissan type, the Nissan Leaf, and we know that it has been in commercial use, and it has also been used in the ship propulsion and the wind power generation. And we say that in fractional slot FSCW machines, there are specific type, which is the FSCW machines with an odd number of stator slots. So the question is why we have the odd number of slots? Because for some specific applications, the requirements for the torque is quite demanding. That means we want to have a smooth torque. That means we want to have the output torque as with a low torque ripple. That means we should make the caulking torque and the torque ripple of the fractional slot PM machines as low as possible. In that case, so the odd number of slots can be a design alternative to maintain a low torque ripple and low caulking torque. Of course, we can use some other techniques such as the rotor magnet screwing or the stator slot, the rotor magnet shaping or the stator slot screwing. They are both the very common techniques for the fractional slot PM machines when we want to have a low torque ripple, but that will increase the machine manufacturing cost, and that in that case, if we want to maintain a low cost, the odd number of slots is a popular choice. But the question is, if we adopt the odd number of stator slot, the UMF will most probably happen. Here, I give you a case, which is a typical machine with odd number slot, which is 9 slot and 4-pole machines. We will see that when will the first, as I just mentioned, when will the UMF will happen? That means if we look at the field distribution of these 9 slot and 4-pole machines, this is the flux line distribution, and this is the flux density distribution due to the MMF only, which is short for the which means from the armature reaction only. We can see that it is very obvious that we can see this asymmetrical field distribution exists in these fractional slot PM machines with odd number of slots. And that is the main reason for the production of UMF. So we will say that the asymmetrical field distribution leads to this unbalanced magnetic force. So this is the 9-slot and 4-pole PM machines. So what about the situations in some other type, like with the same slot number but different pole number? This is a question here, and we will talk about in the following. So the first question is, when will the UMF happens? So the question is, as I just look at that 9-slot and 4-pole machines, that we say the asymmetrical field distribution happens. So the question is, will it must happen? That means, will this UMF must happen in fractional slot PM machines with odd number of slots? Is this UMF I mean, it is if that means if we have the odd number of stator slots, then will it 100% sure will have the UMF? So the question is no. So let's look at the existence criterion of the UMF. Here, we first use the analytical way in order to get a quick analysis of the L-gap field harmonics in both the open circuit and from the armature reaction. We use this simplified model in order to get analytical expressions of for the armature reaction for the PM MMF, which is multiplied by the permeance function. Then we can get the flux distribution in the L gap. We can see that the open circuit magnetic field contains both the PM original harmonics and the PM modulated harmonics, which means that this PM modulated harmonics is the result from the stator slot, which means the stator slotting effect causes these modulated harmonics. And similarly, we also have the MMF original harmonics, which is from the armature reaction. And also we have the MFF modulated harmonics, which is the result of which means the MF original harmonics modulated by the stator slotting. Here is I give you two tables of the attributes of L-gap field harmonics and the attributes of magnetic traveling stress, because we know that the unbalanced magnetic force will ultimately, if we trace back to its original causes, we know that it is from the magnetic traveling stress. In that way, we can list all the harmonics, all the sources of this traveling stress, and then also the field harmonics. And then we will find that we have two conclusions here. That is, only the first order component of the magnetic traveling stress contributes to the UMF. This is the future of the triangular function. This is a character of the triangular function. We can see that only the first order component of traveling stress will have the value of this equation. And if we look back, we will say that only the field harmonics with the order differing by 1 will contribute to the UMF, which means this first order component traveling stress, this traveling stress comes from the L-gap field harmonics, and so what is the conditions here is that only the field harmonics with order different by 1 will contribute to the traveling stress with first order, and this first order traveling stress will finally contribute to the UMF. So the existing criterion is very simple, that if we can find in the L gap whether there is the field harmonics with the order different by 1, then we are definitely will find the UMF in these fractional slot PM machines. So the next step is very simple, is that we try to find each type of fractional slot PM machines to see whether there's two adjacent. We can try to call these field harmonics with adjacent harmonics. If we can find these adjacent harmonics, then we will say there will be harmonics, there will be UMF. Then if we do not find these harmonics, then we will say that there will be no harmonics. I think that is a very simple way to determine whether the UMF will exist. So then we can, it is very simple here that we try to list the open circuit harmonics of the in the harmonic order in the L gap field, and we will say that only when slotting effect is considered, then the UMF will be generated. That means in the open circuit, UMF will only be generated by the stator slotting effect. We can think about it in another way. If we do not have stator slotting on the open circuit field, then the L gap harmonics in the L gap field will have no chance to have adjacent harmonics, which means, like, because for the open circuit harmonics, the harmonic order is 1, 3, 5, 7, so there will be no chance to have the UMF. But if we have a slotting effect, this slotting effect will modulate the adjacent harmonics, which will interact with the original PM harmonics, and then the UMF will be generated. But the second one is only when the machine periodicity is 1 will the open circuit UMF will exist. So this is the open circuit condition. Then let's look at the on-load conditions here. That we will say that when the machine periodicity is 1/1, no additional UMF will be produced. That means even if we have odd number of slots, but if luckily the machine periodicity is over 1, like 3, 5, 7, then no additional UMF will be produced. And the second one is when the machine periodicity is 1. So the question is why we have additional UMF. That is, if we have the machine periodicity is 1, that means like the nice, for example, if we have the 9 slot 2-pole, 9 slot 4-pole, and more normally we have 9 slot 8-pole, 9 slot 10-pole. This means that when the machine periodicity is 1, both the self-interaction of armature reaction harmonics and the mutual interaction with the PM fundamental harmonic will exist in this scenario. So the additional UMF brought by the armature reaction must exist here. So this is from the analytical way, this is an analytical way to analyze the UMF. So let's look at a special case. Like here we give you the 9 slot 6-pole PM machines. This machine topology is very, very special because on the one hand, we have a 9 slot, which is an odd number of slots. But on the other hand, we have 6-pole, which means if we combine it together, this actually is the sub machine is a 3-slot 2-pole machine, which definitely has the UMF. But what about the situation in 9-slot 6-pole, which means, as I just mentioned, this machine is a machine with a machine periodicity over 1, which is 3 here, we will see that in the space, for each submachine, which I mentioned is a 3-slot, 2-pole machine, it definitely have the radial stress or the tangential stress. But if we look at it in the whole way, we will see that this radial stress or tangential stress in each of the submachines are cancelled by each other because they are lag each other by 120 degrees. That is very similar to the 3-phase system. So that is why they can cancel by each other. And that is why we have the negligible UMF in this very special type of fractional slot PM machines. We will say that the canceling effect exists in this between the radial, both the radial and the tangential stress in each of the submachines. But we should note that only when we have the machine periodicity is not 1, which means if we have the machine periodicity is 1, then we cannot divide the machine into those submachines, like the 3-slot 2-pole machine or the 9-slot 8-pole machine. The whole machine is a submachine, so it cannot be divided by a number of submachines. So that is why they cannot cancel each other. So that is from a physical way to understand the existing criterion of the UMF in fractional slot PM machines. So this is the first question. So second question is how this UMF is influenced. We will see that in some specific type of slot pole combination, will this possible? Some slot pole combination is smaller, some slot pole combination is larger. So let's look at it. So the question is the influence of slot pole combinations on the value of those UMF. That means if we do have the UMF in the machine, how those choice of slot pole combination influence them, how we choose a reasonable slot pole combination. Here, I give you 4 cases from they both have a slot number of 9 slots, but different pole number from 2, 4, 8, 10. Then we can see the result. Here, I give you the waveform of both the radial stress and the tangential stress of the first component. As I just mentioned, only the first component of the radial and tangential stress will contribute to the UMF. And then we'll amazingly find that for the investigated 4 PM machines, we will see that there exists the additive and canceling effect between the first component of the radial stress and the tangential stress. We will see that for the 9-slot 2-pole and the 9-slot 8-pole, the resultant component of the radial stress and the tangential stress are in the same direction. But by contrast, for the 9-slot and 4-pole and the 9-slot and 10-pole, the resultant radial stress and the resultant tangential stress are in the reverse direction. That means they are cancelled by each other in the space. So that is why the final UMF will be smaller if we have those cancelling effects. But that is also depends on the value of those radial stress and the tangential stress. So then we will look at what is the value here. The amplitude of the radial stress and the tangential stress, we will see that the amplitude of the contributing MF harmonics in 2-pole and 4-pole are smaller than the 8-pole and 10-pole, which means if we have a very few pole number like 2-pole and 4-pole, the amplitude of those contributing harmonics is smaller. So if we combine those amplitude effect and the canceling and additive effect together, we will finally to see the resultant UMF. We will see that for the 9-slot 2-pole, although it is the additive effect between the radial stress and tangential stress, but because the amplitude of both two stress are very small, so the final stress, the sum of radial and tangential are still very small. But by contrast, for the 9-slot and 8-pole, because the amplitude of the radial stress and tangential stress are already very large, and we know that additive effect exists between the radial and tangential stress. So the sum of these two components become very large. That is why the UMF in the 9-slot 8-pole are much larger than other slot pole combinations. We will say that the machines with a few pole number, like 2-pole and 4-pole, because they have the very small amplitude of the contributing traveling stress. So no matter whether it is additive or canceling effect, the resultant UMF are comparatively smaller than the other slot pole combinations. So this is the second question. So after we know that the existence criterion, the UMF, when the UMF will happen, and how the UMF is influenced by those slot pole combinations. So the final question is how we reduce them, how we try to mitigate the UMF as much as I can. So here I give you a very simple techniques. That is, we use the multi-layer winding configurations that we try to, the basic logic here is we try to reduce the contributing harmonics in the MMF, because we know the MMF will bring additional UMF to the machine. So the key issue is how we reduce the contributing harmonic, such as the subharmonic in those MMF. Then we can reduce the UMF. Here we can see this is a conventional double layer configuration in a 9-slot 4-pole machine that we can use the 4-layer winding, which have a shift angle with 20 degrees, and we can also have a shift degree of 40 degrees here. Then we can, the most important question is how we get the MMF. There are two ways. The one way I propose here is we can calculate use the winding function, use an analytical way. But what I want to emphasize here is not this type. What I want to propose you here is that how we can get MMF in the GMAX software, and how we can use the FE software to get the flux densities in the armature direction. Here is we use the frozen permeability method, and I think this method is a big advantage of the GMAX software, because we, honestly speaking, I can't find more better ways to use the frozen permeability method other than GMAX. This is the basic procedure of this method. We use the nonlinear FE and with all excitations, which means we put the PMs and the armature reaction, which means we inject current and we use the PMs in the first FE calculation. And then the second step is we save and freeze. We use this tool in the box, which is indicates the frozen permeability. We put those frozen permeability in both the stator and the rotor iron. That means we can freeze and save the permeability condition on the on-load under the on-load condition calculation. So the third step is that if we want to see the MMF flux density, that we put those results of those frozen permeability of the stator and the rotor back into the stator and rotor, which means we revolute the same exact permeability for the on-load condition to inject those permeability into the stator and the rotor iron. Then we can get an exact value of the flux densities due to the MMF distribution from the MF excitations here. Then we can use the FFT tool to analyze the specific value and harmonic order brought by the MMF in GMAG. I think this method is very recommended for in the GMAG use because it is very simple. And then the second one is we can use it very quick and get a very exact result of the flux densities due to the MMF. And then we can see the result, and we'll clearly see that for the 4-layer configuration, you can see the harmonic value of the amplitude of the value of the subharmonic, which is a main contributing harmonic, has obviously decreased a lot, significantly reduced. And if we look at the unbalanced magnetic force, and we can see the average unbalanced force has reduced by 20% compared to the 2-layer winding configurations. So here's the final conclusion, that we determine the existing criterion of the fractional slot PM machines with an odd number of slots, and we have found that there exists a special type of FSC PM machines with odd numbers of state slot, like 9 slot and 6 pole, have negligible UMF for this specific type of PM machines. And we also investigate the influence of the slot pole combinations on the value of the UMF. And finally, we propose the multi-layer winding configuration for the reduction of the UMF. So that is the general my presentation for this topic. So the next will be the question and A section.
Thank you. Thank you very much for your nice presentation. So yes, we can go through some of your questions. So you can still ask your question through the chat or the Q&A panel in Zoom or Wova.
Shall we stop
yes.
sharing or to see the question? Or
I will ask the question to you. So if you want to go back to the slide, you can take care of it. So now we have one question and one comment, would say. So the question is, does the study applies to delta wounded motor?
Which one?
I think it was, can you go up again? Yes, I think it was on that part.
Yeah.
Yeah, so the question is, does the study applies to delta wounded motor?
What?
Does the study applies to delta wounded motor as well?
You mean does this effect apply to delta Y connection?
Yes, I think, yeah.
Yeah, I think because we know that for this 9-slot 6-pole combination, we have the key issue is that we have a symmetrical field distribution of this specific type. Even if we change the connection, it still applies because the asymmetrical condition doesn't change. That is my answer.
Okay, thank you. So then it's not really a question, it's more a comment, but I will read to you and maybe you want to answer that. So UMF is generated if you have a high winding factor for two directly adjacent orders in the winding factor spectrum.
Yes, that is why in this section slot, that is why we can see why the slot for the 2-pole and 4-pole is smaller, because the winding factors for the first and second harmonic of this specific harmonic is smaller than the fourth and fifth harmonic. That is the winding factor effect here. Yes.
Okay, thank you.
Yeah.
Other comment, the harmonics and field on the presentation looks like a wounded motor. Do you agree with that?
Pardon?
The harmonics and field on the presentation look like a wounded motor. Wounded motor.
Sorry, what motor?
Maybe you can open the question and answer panel in Zoom.
Let's look at
it. Just click on Q&A.
Okay. So.
Okay, maybe it's my fault. I didn't.
Yes, the harmonics is Y connected. Yes, which is a normal connection for most of the machines. It's Y connected.
Okay.
Yeah.
Okay, thank you. Any other question? I think we have answered to all of them so far. I'm just checking.
Oh, hello. Yes, Yves speaking. Can you hear me?
Yes, we can hear you, Yves.
Yes. Thank you for your presentation. I have a question regarding the frozen permeability. Maybe you should not know that there is a new feature now in JMAG, and you can actually capture. So I don't know how you capture your data, but if you use some arc section, now you can select which part you would like to take into account. I mean, for example, if the MMF are coming from this winding or this other windings, or only from this this part. So I think this could be useful as well, and maybe you don't need the frozen permeability anymore.
Okay.
That's just a comment. Maybe you can have a look.
Okay, I will see it in the new version. Yeah.
Yeah.
You mean from the one specific coil, the MM from the specific coil?
Yes.
Okay. That
you can keep driving the other one, keep the current on the other one, but then you capture the MMF just due to one coil, for example, the U, or I don't know, something like that.
Okay.
So there is a new checkbox at the bottom when you create some arc section, where you can select which part you would like to, in fact, isolate the B coming from this winding and not the other one.
Okay.
Thank you, Yves. We just got another question. Did you analyze the effect of unbalanced or random magnet spacing in order to break the harmonics?
Yeah, I think this is a good question. That because here we have asymmetrical arrangement of the PMs. That is why we say that there are if we do not have slotting effect, there will be no EMF. So in the situation of asymmetrical arrangement of the PM rotor PMs, such as which is a consequent pole PM machines, then in that case, then we'll have an even odd number of harmonics. Then the open circuit UMF will be larger. And I think the random magnets will change the harmonic component on the open circuit. That will also make a great impact on the final UMF. Yeah.
Okay, thank you very much. So I think we are done for the questions. So thank you again, you, for your presentation. Do you want to add any other comments before you stop the session?
No, I'm good.
Okay, great. So I will just share a few information before you leave all. That's why I will share my screen. Give me 1 second. Okay. Oh, okay, let's change this. Okay, so the first thing I would like to share is that if you want to learn on the GMAG usage, we are organizing an interactive complete training program from November 2020 to January 2021, composed by nine modules from beginner level to a more advanced level. So you can choose the module you want to follow. It's an online training composed by several online sessions in small groups. So the maximum of group will be 4 participants. So we want to keep very small groups to have a good interactivity with the trainer. So you can build the training program you want depending of the module you want to attend. So this is quite interesting for the end of the year, and we propose this this training program to you. So I will put the link to registration on the chats just right now, but you can find information on our website www.sporosyssolution.com, and let us know if you have any question. So, and then for this for today, it was the last presentation. The next presentation is tomorrow at 11 a.m. French time, CEST, and will be about a demo session of GMAG V20, so the next year version. And it will be given by Juan Marcano, one of our GMAG engineer. And then we will have another presentation. It will be more a tutorial on how to create a geometry template in GMAG using Python scripting, again with Juan. This will be at 12 o'clock. And then at 3 p.m. Paris time, we'll have a presentation on PECIM implementation of a dynamic model of 3-phase induction motors by the University of Catania in Italy. And finally, at 4 p.m. in the afternoon, Paris time, another presentation about additively manufactured copper winding, calculation process optimization potential from TU Freiburg in Germany. So when you are trying to connect to a presentation, if you have some trouble or if it doesn't start at the time, please remind remind you to refresh your browser, your web page, and the presentation should start. So let us know if you have any question. You can ask question at any time on the Wova platform. And thank you again for attending this presentation. Have a nice day, or bye-bye.